Hey guys, so now that we've learned how to solve absolute value equations, now it's time to learn how to solve absolute value inequalities. But I like to start with an easy absolute value equation that I'm sure you know how to solve. Think about the equation, the absolute value of x is equal to 5. And I'm sure you already know what the solutions are to this. It's x could be 5 or x could be negative 5. But what this question is asking is it's asking, please find the numbers such that their distance from 0 on the real number line is exactly 5 units. Now, what numbers are that? Well, of course, 5 and negative 5. These two numbers are exactly 5 units away from 0 to the right and to the left. But what if we now change our original problem and we say, let's solve the inequality, the absolute value of x is less than or equal to 5. Now how does that change things? Well, maybe let's think of some numbers that'll work. I think 5 will work, 4, negative 3, negative 2, but maybe like negative 6 I don't think negative 6 would work. And 8, I don't think that would work either. And maybe you can think of what numbers are going to be solutions to this, but let's think about this in terms of distance from 0 on the number line. What this inequality is asking us for is, please find all numbers such that their distance from 0 on the real number line is less than or equal to 5. It's at most 5. And visually, I think that means, well, find all numbers that are no farther away from 0 than 5 on the right, and no farther than 5 away from 0 on the left. So actually, I think this is all numbers between negative 5 and 5. And so this absolute value inequality has a solution set. Negative 5 is less than or equal to x is less than or equal to 5. So a totally different kind of result now that we're dealing with an absolute value inequality. Let's try another one real quick. What about solving the absolute value of n is less than or equal to 8? So now what we're looking for is we're looking for all numbers on the number line whose distance from 0 is less than or equal to 8. It is no more than 8. It can be up to 8, but not any farther from 8. So let's see, on the right-hand side for positive numbers, you can go all the way up to 8. But if you go higher than 8, that's too far. The absolute value is going to be too big. And if you think of to the left of 0 on the number line, you can go all the way down to negative 8. But negative 8 is as far as you can go. Once you go beyond negative 8, your numbers are too large in magnitude. They're too far away from 0 on the number line to be solutions. So numbers that make this statement true are all the numbers that lie between negative 8 and 8 on the real number line. And we can write that by saying negative 8 is less than or equal to n is less than or equal to 8. So perhaps we're seeing a trend here that if we have the absolute value of some number, some quantity, something, if we have the absolute value of that is less than or equal to a number, well, you just, positive 5 and negative 5, whatever this thing is has to lie in between them. Or positive 8 and negative 8, whatever this thing is, it has to lie in between them. A quick note, I want you to answer me this. What if you had something like the absolute value of w was less than or equal to negative 3? What do you think about that? Well, I don't think it's possible to have an absolute value that's negative at all. So it's impossible to have an absolute value of some number be less than negative 3 because it'd have to be negative. So this is an impossible statement, or I'd say that inequality has no solutions. So keep that in mind. If you ever get to the point where you've got the absolute value of something is less than or equal to a negative number, or just less than a negative number, ain't gonna happen. No solutions at all. So now that we've got the kind of foundations ready, let's go ahead and let's solve a slightly more complicated version of one of these absolute value inequalities. Something like solving 2 plus 3 times the absolute value of 2x minus 5 is less than or equal to 29. Now I know that we went really big here. This is way more complicated than either of these that we've looked at so far. But the strategy is actually really, really similar to what we did with absolute value equations, where the only difference was this is an equal sign. our first primary goal is let's isolate this absolute value by itself. Let's treat it as an object and let's isolate it. And in order to do that, the first thing I want to do is I think subtract 2 from both sides of this inequality, yielding 3 times the absolute value of 2x minus 5 is less than or equal to 27. To isolate this absolute value, I think we need to divide both sides by 3. When we divide by 3, we know that 3 over 3 is 1, so we're just going to have a 1 absolute value of 2x minus 5, and that is absolutely what we'd like. All right, now that we have our absolute value isolated, and I'm going to move this a little bit more towards the center. Okay. We are now in a position where we say, hey, here's a number, 2x minus 5. It's a number. I don't know what it is, but I know that this number, 2x minus 5, it has an absolute value less than or equal to 9. 2x minus 5's distance from 0 on the real number line can be no greater than 9. It has to be less than or equal to 9. And so what that means is 2x minus 5 has to lay between 9 on the right for positive numbers and negative 9 on the left. So immediately, I would say that this inequality translates to, well, negative 9 is less than or equal to 2x minus 5 is less than or equal to 9. Right? 2x minus 5 has to lie in this region right here. It must be between negative 9 and positive 9. All right, I'm going to get rid of these guys for a moment. All right, we'll bring this on down. And now what we've got is we've got one of those compound inequalities that I think we know how to solve. And there are a number of ways to solve this. We can split it up into two separate inequalities, separated by an and statement, or I'm going to solve this kind of on the fly with both at the same time. So I'm going to add 5 to all components of this inequality, yielding the new inequality, negative 4 is less than or equal to 2x is less than or equal to 14. And we divide all portions of this inequality by 2. We are left with negative 2 is less than or equal to x is less than or equal to 7, which means that in order to be a solution to our original statement, our x coordinate must lay between negative 2 and 7. And it can include 2, it can also include 7. So right here is our solution set, which it's always a good idea to graph on a number line as well for our reader. If you want to check your answer to make sure that these are solutions to our original inequality up here, you can pick any number between negative 2 and 7 and see if it works. Maybe 0. 0 is my favorite number to try. Let's see, if x were 0, this thing would be 2 times 0 minus 5 is negative 5. The absolute value of negative 5 is 5. 3 times 5 is 15. 2 plus 15 is 17, which is definitely less than or equal to 29. An even better check is to try these endpoints. See if negative 2 works. And negative 2, if you were to substitute it in for x, should make this left-hand side exactly equal to 29. And if you try 7 in for x, you will find that this left-hand side is exactly equal to 29, which shows that these two numbers are indeed the boundaries of our solution set. So now we kind of see what's going on here. We kind of got the idea of how to do this. Let's do one more together, and then I'm going to have you try one on your own. How about solving the inequality 17 plus the absolute value of x plus 12 is less than or equal to 6. So once again, first things first, we want to isolate our absolute value, and the way to do that I think is going to be to subtract 17 from both sides. So minus 17, minus 17. The absolute value of x plus 12 is less than or equal to negative 9. Wait a second. That's impossible. That can't work. That doesn't happen. Boom. Immediately we see we have the absolute value of something less than or equal to negative 9. Boom. Not going to happen. No solution. So I just urge you to keep that in mind. Let's write this a little bit neater, shall we? Keep that in mind as you're making your way through, that if this is ever the case, you are done. There are no solutions to that inequality. Okay, let's have you try one on your own now. Why don't you try to solve the inequality negative 6 is plus 2 times the quantity of x minus 3 is less than or equal to 4. You know what? Let's make this less than 4, just less than 4. Okay, so when you pause the video, give that guy a try, and when you're done, unpause the video. Let's see what happened. Okay, so I think, again, the first thing we want to do is isolate our absolute value. And we're going to do that by first adding 6 to both sides of our inequality. We have 2 times the quantity of x minus 3 is less than, let's write that a little more neatly, less than 10. I think we need to divide by 2 on both sides. 2 divided by 2 is 1. Amazing. And we have isolated our absolute value of x minus 3, and that must be less than 10. So x minus 3, whatever number this is, its distance from 0 on the number line must be less than 10. It must be between negative 10 and positive 10. That's where x minus 3 can reside. Lucky for us, this is a nice, quick finishing up of the problem. Just going to add 3 to all components, and we find that the solution set for our original inequality are all numbers such that they lie between negative 7 and 13. And let's graph this on a number line because I think that is definitely a good practice. And we got 0, negative 7, 13. And note that this kid, oh good God, look, you know what I did which is so bad? This was a strictly less than 10. So this needs to be a strictly less than, and a strictly less than, and a strictly less than, and a strictly less than, meaning that we are going to have some open circles on both of our boundaries for our solution set. So my apologies about that, but that's I hope that went well for you, and that's kind of the gist of solving these types of absolute value inequalities. But there is another type of absolute value inequality that I'd also like us to be aware of. What happens if we're faced with something like the absolute value of x is greater than or equal to 5? So let's see. Let's write a number line. And what this statement says is we are looking for all numbers whose distance away from 0 on the real number line is at least 5. The closest you can be to 0 is 5, or your distance can be greater than 5. So let's think. To the right of 0, well, these numbers are too small. They're too small. They're too close to 0. They're too close to 0. 5 is the first number that will qualify as a solution to this inequality. And then 6, 7, 8, 9, 10, forever and ever are also going to work. So these numbers out here to the right, these are solutions to that inequality. What about negative numbers? Well, negative 1 is too small. Negative 2 is too small. Negative 3 is too small. Negative 4. Negative 5 is just a big enough negative number. Its absolute value is just big enough to satisfy this inequality. Negative 6 is big enough. Negative 7, forever and ever and ever. And so all of these numbers out here are also going to satisfy that inequality. And so we find that with this absolute value inequality, where the absolute value of x is greater than or equal to negative 5, we find that x must be smaller than, less than or equal to negative 5, or it must be greater than or equal to 5. And note that I kind of wrote these inequalities in such a way that they kind of mimic what's going on the number line. And in general, this is going to be the case. We'll do another quick example right now in dark green. So what about, the absolute value of n is greater than or equal to 8? Well, okay, that means that we're looking for all numbers such that their distance from 0 on the number line is at least 8. So if we think to the right, well, positive 8 is the smallest positive number that will make this true, right? 1, 2, 3, 4, 5, 6, 7, 7.9, 7.95. They're all too small, but 8 is the smallest positive number that can make this work. So 8 is going to qualify or satisfy this inequality, and every number greater than 8 as well is going to work. For negative numbers, negative 1, negative 2, negative 3, negative 7, negative 7.5, negative 7.9, none of these have a great enough absolute value. None of them have a great enough distance from 0 up until Boom. Negative 8 is the smallest negative number, if you will, that will satisfy this inequality, and any larger negative number to the left on the number line will satisfy this inequality. And so we see that for this inequality to be satisfied, it must be the case that n is less than or equal to negative 8, or, and this is a big deal, or 8 is less than or equal to n being greater than or equal to 8. And so this is how we're going to set up these sorts of absolute value inequalities. On a side note, just like before, what if I had something like the absolute value of w is greater than or equal to negative 4? Well, you know what I'm thinking? If I substitute any real number in here, the absolute value is going to be at least 0, probably going to be positive, and no matter what, it's definitely going to be greater than or equal to negative 4. And so if you ever have this sort of absolute value inequality, the absolute value of something is greater than or equal to a negative number, boom, all real numbers. There's nothing that won't work for this inequality. So all real numbers. Of course, we got to be really careful, because if this were a less than or equal to, then it would be no solutions. But since it's a greater than or equal to, it is all real numbers. So definitely something to keep in mind. So let's do some practice problems and see how these ones work out. So these are no different from what we did before. How about trying to solve and graph the absolute value inequality? Negative 4 plus 2 times the absolute value of x minus 6 is greater than or equal to 12. Of course, our first objective is to isolate this absolute value so that we can then kind of interpret what make an inequality just like we talked about up here. So we want to isolate that absolute value first. So in order to do so, I think we should add 4 to both sides of this inequality. We got 2 times the absolute value of x minus 6. Let's draw that a little closer. Is greater than or equal to 16. If we divide by 2, 2 divided by 2 is 1. Amazing. And we end up with the absolute value of x minus 6 is greater than or equal to 8. So there goes 8 again. That's kind of nice. So it means that x minus 6, its distance from 0 on the number line, it has to be at least 8. X minus 6 has to exist either out here to the right of 8 on the real number line, or out here to the left of negative 8 on the real number line. And it can be exactly 8. It can be exactly negative 8. And so let's split up, or let's rewrite this absolute value inequality as a compound inequality that it implies, namely that x minus 6 could be less than or equal to negative 8, or it could be the case that 8 is less than or equal to x minus 6. And now we've got two pretty easy inequalities to solve, and let's go ahead and do it. So plus 6 plus 6. So x could be less than or equal to negative 2, or x could be, or I'm going to say 14 is less than or equal to x. And if we were to graph this on a real number line, we get a solution set that looks like this. And it's kind of an awkward one. There's no nice, succinct way to write it. Kind of just, this is how you write your solution set, because it's comprised of two distinct intervals of numbers. And so that is how we solve these sorts of inequalities. So let's have you try one. Or you know what, actually I'm going to walk you through one more before I have you try one. Let's try solving the absolute value inequality 3 minus 4 times the absolute value of negative 2x plus 3 is less than or equal to 27. Yowza. And note to self, we've got to be real careful. I see a negative 4 that we're going to eventually divide by, a negative 2 that we're going to eventually divide by. Whoa, so we're going to have to be really careful about switching the directions of our inequalities. Once again, let's isolate this absolute value inequality right now. So I think let's subtract 3 from both sides. So we got negative 4 times the absolute value of negative 2x plus 3. All of that is less than or equal to 24. And note to self now, when we divide both sides of this inequality by negative 4, that is going to have the effect of switching the direction of that inequality right there. So I always like to make a little note to myself so I don't forget. 24 divided by negative 4 is negative 6. Okay, that's all right. So now we've got the absolute value of negative 2x plus 3 is greater than or equal to negative 6. Wait a second. That's impossible. Or rather, excuse me, no matter what x is, it's actually the opposite of impossible. Whatever x is, and whatever number this is, its absolute value is going to be at least 0, if not a positive number. This is definitely going to be true no matter what. So our solution set here is all real numbers. Now, just to get some practice, imagine that the problem was set up slightly differently so that instead of getting negative 2x plus 3, or its absolute value is greater than or equal to negative 6, what if it were the absolute value of negative 2x plus 3 were greater than or equal to positive 6? Okay, so this is slightly different. So let's pretend that we had this and we had to solve this inequality. Well, this means that negative 2x plus 3, whatever number that is, its distance from 0 has to be at least 6 away. So I think that that means that negative 2x plus 3 would have to be to the left of negative 6 on the number line, or it could be to the right of positive 6. Those are the two regions in which negative 2x plus 3 could reside. And now we've got just two kind of simple inequalities to solve and graph. So let's do it. So subtracting 3 from both sides, negative 2x is less than or equal to negative 9. When we divide by negative 2, just like always, we are going to have to switch the direction of that inequality. Let's see what the implications are. All right, so x could be greater than or equal to 9/2, or let's solve this side. Let's subtract 3 from both sides. 3 is less than or equal to negative 2x. And when we divide by negative 2 here, let's see, we must remember to switch the direction of that inequality. We end up with negative 3/2 is greater than or equal to x. And so let's graph both of these on a real number line. So let's graph this guy right here in blue. X is greater than 9/2, so about 4.5, greater than or equal to. And the other one we'll do in green. X is less than or equal to negative 3/2. Oh, so just as we suspected, we end up with another one of these solution sets comprised of two distinct sets of numbers. And there's no better way to write our final answer to the reader than just circling these two separate statements, because there's nothing more we can do. There's no more succinct way we could express our solution set algebraically. So I hope that this was helpful, and I hope you enjoy it.